to start the class and to start recording. Let me raise this desk just a little bit. And let me remind you of what the conditions on the delta function are. Here I can bring this over from the other screen. The idea here is that if we have a set of eigenfunctions with eigenvalues, weight function, and it's a Sturm-Liouville system, it's complete in the mean in the domain, and it is complete if every function can be represented by a generalized Fourier series, that is to say, a sum of all the eigenfunctions with coefficients. As I said, it's complete in the mean if this sum converges in that way. The eigenfunctions are orthonormal in the sense of this integral. When you weight the integral by means of the weight function rho, the weight function rho is the function that occurs when you take the differential equation and put it into self-adjoint form. Rho pops up on the right-hand side, and the coefficients then AI are given by these integrals, and if you write f as the sum of AI ui of x, you get this sum here. The rho can obviously be factored out, and so you have this sum here. That is to say, you have a representation of the delta function in which is rho of y times this sum of ui of x, ui of y. And the ui's are the eigenfunctions that are orthonormal when weighted by rho, and they have eigenvalue lambda. Okay, so that is why we have this. In the case of Legendre's equation, the weight function is just the number one, and so to make them orthonormal, we divide by, we multiply by 2n plus 1 over 2. And this series, as I said, I did an actual sum of this thing using MATLAB, and I got this representation of the delta function. So this has, I think, 4 times as many terms as are described in the sum in the book. The Legendre polynomials are, of course, normally just defined as polynomials, powers of a constant plus another constant times x plus another constant times x squared and so forth. If we change variables, though, setting x equal to cosine theta and 1 minus x squared equal to sine squared theta, then what we find is that d by d theta is minus sine theta d by dx. So d by dx is minus 1 over sine theta d by d theta. And then Legendre's equation takes this form. And this is the form that one sees it in elementary physics books, because there one isn't focused on Legendre polynomials, one is focused on Gauss's law. And so you have, and in particular, when you have no charge density, then you have the Laplacian of the scalar potential vanishes if you have no charge density and, of course, no time dependence. And then so then you have equations which involve well, Gauss's law itself involves 1 over the distance between two, three vectors x and y, say, and that's where that is the generating function for the Legendre polynomials. And the main recurrence relation, the most important one, comes from writing the generating function. The generating function is often written this way. You take the derivative with respect to t, and you get this expression, and then you can rewrite that expression as, of course, what I sort of left out there is, let me just see if I can put this in. Whoops, why? Okay, so let me switch to blue, and so the point here is the g of t and x, which is 1 over the square root of 1. Good God, what happened? What happened here? This, I don't know. Apple just makes things just too goddamned cute. The problem I'm having may be that I upgraded to Ventura today, and this means presumably that everything is slightly different. So let's see if I can. All right, I'm going to collapse that. This is then 1 minus 2xt plus t squared. That's t squared. And that's equal to a sum t to the n pn of x, pn n of x. And now you differentiate that with respect to t, and you get this expression. You rewrite that in this way by multiplying both sides by 1 minus 2x, well, by this expression, and then what you get is these two forms. That is to say, this you get 1 minus 2xt plus t squared multiplying this is then equal to x minus t divided by the square root, but that's g. On the other hand, g is the sum t to the n pn of x, and we still have this x minus t. And then if you compare all the coefficients of t to the n, and because this is an important recurrence relation, if Apple will let me, I will try to show you what you do here. You see, over here, you want to equate powers of t to the n. And so on this left-hand side, what you've got is, if you want t, let's consider the coefficient 1, then that multiplies tn minus 1. So in order to get t to the n, you have to shift n to n plus 1. So you get n plus 1, pn plus 1 from the times t to the n, but I'm going to leave out. All right, I'll put in the t to the n. Then from the term here, minus 2xt, well, that just gives you minus 2nx pn t to the n, because the t turns tn minus 1 to tn. And then you have one more term, which is the t squared term. Well, t squared takes this to n plus 1. So you have to go down 1 in n. So you get plus n minus 1 p n minus 1 t to the n from this term. And then you want to set these equal to the right-hand side. And the right-hand side gives you, first of all, x pn t to the n from the first term, and then minus, and now to get n plus 1, you have to go down 1. So you have minus p n minus 1 t to the n. And now putting all that together, what you get is this expression here. In other words, get rid of the, so let me now get rid of all these t to the n terms. So getting rid of the t to the n terms, in other words, factoring out t to the n, you have that expression. And then if you combine all these things appropriately, you see what you have is, what you have, let me switch to red maybe. What you have then is pn plus 1 is 1 over n plus 1. And then what you've got on the right-hand side is 2xn pn plus x pn minus pn minus 1 minus n minus 1 pn minus 1. Well, all of those combine to form 1 over n plus 1 times 2n plus 1, that's a 2. 2n plus 1 x pn minus n p n minus 1. And this is this recurrence relation. And as I said, this is the quick way to build your Legendre polynomials. You can start with p0 equal to 1 and p1 equal to x. And then with that, you can generate them all from this recurrence relation very quickly. So I think that's how computer programs for the Legendre polynomials, how they compute the Legendre polynomials. Well, last time we looked at the generating function again and used it to find special values. And if you set x equal to minus 1, you get this expression. This is just 1 plus t squared. And so 1 over the square root of that gives you 1 over 1 plus t. That's this sum up to infinity, at least for t less than 1 in absolute value. And this then is, has got, the generating function tells you that this is t to the n times pn of minus 1. And so that tells us then that pn of minus 1 is minus 1 to the n. And if you go to t and 1, you find pn of 1 is 1, and that was, of course, the original condition. And you can then see that if you, this is just the property of the useful property of the generating function, but this generating function you see here, if you, well, where is it? There was an, all right, let me get back to the generating function itself. Is so what we have here is the g of t and x is equal to 1 over the square root of 1 minus 2xt plus t squared. So this is equal to g of minus t minus x. And so that's why we can say that this is even under reflection of both variables. So g of t and x is g of minus t minus x, and now we put minus signs into this, and we get that. And what does that tell us? That then says that Pn of minus x has to be minus 1 to the n times Pn of x. And so then you set x equal to 0, and you get that when n is odd, you get that P of 0 is 0. So P2n plus 1 of 0 is 0. And with a great deal more effort, which frankly I don't remember how I did this, but or how I got this, but this is the formula for P sub 2n of 0. And one can also show that the absolute value of P sub n of x is always less than or equal to 1. That's something that we saw in the just the original picture. Let me see if I can bring that up on the other screen and then show you. Yeah. If I bring this over, here are the first 20 Legendre polynomials, and you see they're all between minus 1 and 1. But it's more effort to show that, so I'm going to skip that. It turns out that the formulas 9.8 and 9.9, that is to say, Rodriguez's formulas for the Legendre polynomials can involve pretty big factorials, and I show how to cope with such factorials in the chapter on statistics. It's chapter 16 or something. And alternatively, if you're just interested in the Legendre polynomials, you can write them this way. And it's a square root of an arc cosine, and then it's a 0th Bessel function. And the argument of the 0th Bessel function is the arc cosine of x, and then you divide by this. So this is not, it's not transparent where that comes from, for sure. And in the limit of log n, it becomes a cosine. Well, all right. I think this is a little bit too far in the weeds. Here, you remember that one of the advantages of the Wronskian is that one can find a second solution for a self-adjoint for an eigenfunction of a self-adjoint differential equation. And what you do is you use this formula here, and so to get the second solution of Legendre's equation, what one finds is an integral like this. But these do not satisfy the boundary condition, which is Pn of 1 is equal to 1. And in fact, you can see that this function diverges as x goes to 1, because as x goes to 1, you have to integrate out to 1, and then you have 1 minus x squared. And then it's multiplied by something that's effectively 1 as x prime goes to 1. So this is a divergent expression. And one expression for it is this. And you see here, it's a log of something singular. But of course, a log is a singular, it's log of 1 over 0 is singular, but logs are the gentlest of the singularities. 1 over x is much more singular than 1 over log x, or log of 1 over x. Now, Schlaefli took Rodriguez's formula and applied Cauchy's integral formula. And so this is the nth derivative. So the nth derivative is 1 over 2 to the n, 1 over 2 pi I, and then you integrate any counterclockwise contour that goes around the point x in the complex z-plane. And of course, this can define the Legendre polynomial at complex x as well. Now, all these cute features of the Legendre polynomials are, and Rodriguez's trick can be, or have echoes or things. One can use other, there are other formulas of other families of polynomials that one can discuss in the way we discussed the Legendre polynomials. In particular, you can have a generalized Rodriguez formula, and there it looks like this, and this W is what we call rho. I should maybe go back to calling it rho rather than W, but you know, W for weight. Anyway, what you do is you have a weight function, you differentiate n times, you have something that's q to the n, where q is some function that vanishes at the two endpoints. These things, when are they polynomials? Well, I guess W and Q would have to be polynomials if these things are to turn out to be polynomials. What you find is that these are then orthogonal on the interval with this, on the interval AB with this weight function. And as long as Q vanishes at the endpoints. Of course, that's at the moment an exercise. Maybe I should go through this exercise. So let me bring up this particular exercise. Right, and this is problem 8. Okay, or exercise 8. Exercise is the Cambridge view of these things. So basically, what we do is we say, maybe I can actually show you this rather than write it for you, because if I write it, it will take longer. So what we want to do is we want to show that the nth order polynomials here are orthogonal on this interval with weight function W of x. And so what we do is we consider this integral, and we have this, the parenthesis n means that we differentiate this thing n times, we differentiate that thing m times, because remember, these things are defined as 1 over W times the nth derivative of W times q to the nth power. And so this means nth power, this means nth derivative. And if you differentiate once and basically integrate by parts, you then have things vanishing at the endpoints, and And so you get this expression here, and these vanish because because here we have q to the n, but we're only taking the n minus first derivative. So there's always a q left over, which vanishes at the endpoints. And so what you get is that this is equal to 0 for n not equal to n. Well, I guess that's a little too complicated to go through in real detail. In any event, what you have here is you generate a formula. Rodriguez's formula generates a family of polynomials. Here, if you take q to be x squared minus 1, and this to be the weight function, and the en for normalization, what you get are called the Jacobi or Jacobi polynomials. They're orthogonal on -1, 1, and they satisfy this normalization condition, and they satisfy this differential equation. And in terms of capital R, capital R equal to this. So this is very much like the generating function of the Legendre polynomials. The generating function for the Jacobi ones are defined in terms of the generating function for the Legendre polynomials. And when alpha is equal to beta, that turns out to be what are called the Gegenbauer ones. And if you then set alpha equal to beta equal to plus or minus a half, you get what are called the Chebyshev polynomials. And if you go down then to alpha equal to beta equal to 0, you get back to Legendre's polynomial. And these things also have rather nice recurrence relations, which allow you to build the higher order ones from the first two. Another family of polynomials is the Hermite polynomials. Here you have q is just equal to 1. The weight function now, though, is an exponential, e to the minus x squared. And the Hermite polynomials are -1 to the n, e to the x squared, the nth derivative of e to the minus x squared. And they're orthogonal on the real line, where you have the weight function there. And they satisfy this differential equation. And the generating function is this exponential. The nth excited state of the harmonic oscillator mass, m, angular frequency omega, is proportional to hn of x, where x is square root of m omega over h bar times q. And q is the actual coordinate, x is dimensionless. If you set q of x equal to x, and you choose this weight function, you get these generalized Legendre polynomials. They're orthogonal on an interval 0 to infinity. And of course, that's an appropriate interval if you're talking about, if you've taken a Schrodinger equation, the time-independent Schrodinger equation in 3 dimensions, which is space we live in, as far as we know. Anyway, the radial coordinate goes from 0 to infinity, and so the interval is 0 to infinity. And in fact, these Legendre polynomials show up in the wave function for the hydrogen atom. They're orthogonal on this interval, satisfy this differential equation, and they have a rather complicated generating function. And the radial wave function for the non-relativistic hydrogen atom, no spin, quantum numbers n and l, is given by this expression here, in which rho, the dimensionless variable, is 2r over n, a0 being the Bohr radius, which is about of the order of an angstrom. Excuse me. Oh. So azimuthally symmetric Laplacians. So the Laplacian, of course, separates in spherical coordinates. We saw that earlier. And if there's no phi dependence, which often occurs, then you can write it as a function of r and a function of theta. And then it'll be a solution of, well, if it's supposed to be a solution of Helmholtz's equation, it will be a solution of Helmholtz's equation if the function satisfies these equations. The R function satisfies this radial equation, and the theta function satisfies this angular equation. And then you can set theta equal to a Legendre polynomial of cosine theta. And so this is PL of what we previously were calling X. Remember to go from the X, which was the defining variable for Legendre polynomials, to theta. You've set X equal to cosine theta. And for k greater than 0, the solutions of the radial equation that are finite at r equals 0 are the spherical Bessel function. Remember, I said to you the spherical Bessel function are rather nice functions. And we'll see when we do the Bessel functions next week that the spherical Bessel functions have a very nice form. You just take sine of x over x and you differentiate and then put back L factors of x, and you get the spherical Bessel function. The general azimuthally symmetric solution of the Helmholtz equation, which was this, that's finite at r equals 0, then is of this form. And the finiteness of r equals 0 is what got us to use these spherical Bessel functions as opposed to functions what are called Neumann functions that diverge at 0. And if the solution can be infinite at the origin, then what you do is you bring in the Neumann functions. Instead of sine of x over x, you have cosine x over x, but they're still very nice functions. And then the general solution is of this form. You have two sets of constants, two sets of functions, and just the Legendre polynomials there. And for k equals 0, which is the case where you have basically Laplace's equation, Laplacian equal to 0, but you're also in the azimuthal case. The radial equation has a very simple form, and it's just r. Well, obviously there's something wrong here. Oh, it's r. You get r sub l is r to the n, so you have to have nn plus 1 equal to ll plus 1, and that means that n is l or n is minus l plus 1. And so the general solution is of this form, and these guys are the ones that are singular at the origin. If the function is finite at the origin, then all the b's go, and you just have r to the l. These are things that you must have seen in a course on electricity and magnetism. If you have no phi dependence, this is the general solution for the and no time dependence. This is the general solution for the static potential of the electric field. If you now set k equal to 0, you get Helmholtz's equation becomes Laplace's equation, and this capital, well, here we're thinking in terms of all three variables, rho, phi, and z. If we set k equal to 0, so that we're in, let us say, empty space, electrostatics, no charge, or at least no charge where there's no charge, you have this you have the k squared equal to 0, and you have the Laplace's equation. So then, if alpha also vanishes, actually, now that I think about it, I don't remember what alpha is here. I guess that alpha is inside this. Well, anyway, what you have now is simply rho d by d rho dpm d rho is m squared p of rho, and phi can be taken to e to the im phi because it satisfies this equation, and or a linear combination of cosine and sine, and what you have left then is this equation, and you have then n squared rho to the n is m squared rho to the n, and so n is plus or minus m. And so the general z-independent solution of Laplace's equation is then of this form. So this is electrostatics in 3 dimensions with no z-dependence. And that's what alpha equal to 0 apparently meant, no z-dependence. And then the general solution is of this form. So to get back to the situation that's of most interest is the spherical, the Laplacian and spherical coordinates, and Laplace's equation in spherical coordinates, which is essentially, if you have electrostatics, Gauss's law, a region where there's no charge, then the scalar potential satisfies Laplace's equation, which the Laplacian of f is equal to 0, and in spherical coordinates it looks like this. And as we saw in the case of separable partial differential equations, we write this as r, an r function, a theta function, and a function of phi, and we can immediately see that the phi function should be just e to the im phi. If you do that, you then get, as theta, you get this equation, which is the equation for the associated Legendre polynomial. And this is not a polynomial in cosine, but it's a polynomial in cosine and sine. And of course, sine is square root of 1 minus cosine squared. So it's basically a polynomial in x and the square root of 1 minus x squared. The differential equation for theta, which follows from this, as we saw in chapter 7, is of this form, and this is in fact a self-adjoint form, and the resulting equation for RL is very simple. Again, this is self-adjoint, and we can set r to, if we set r to the L equal to r to the n, we again get nn plus 1 is LL plus 1, and the solutions are n equal to L or n equal to minus L minus 1. And so then what we have is the general solution to Laplace's equation. And we have an r to the L, an r to the minus L minus 1, this quantity theta of Lm, which is somewhat complicated, and then e to the im phi, which is quite simple. So it's the angular dependence that's a little bit complicated, but it's not it's not a nightmare by any means. As you go to infinity, R to the L typically diverges unless L is equal to 0. On the other hand, these guys diverge at R equal to 0. So depending on what the region is, you would have different coefficients here. So Helmholtz's equation then the solution would be R, theta, and phi, and the radial equation then is satisfied by a linear combination of spherical Bessel functions, either the ones that arise from sine x over x or the ones that arise from cosine x over x. So these guys are singular at the origin. You can set phi equal to e to the im phi, and if you do, you then get that theta satisfies what's called the associated Legendre equation. And it is then a multiple of what's called the associated Legendre polynomial, PLM of cosine theta. And this factor is, so we have a nice normalization condition. So what are these associated Legendre polynomials? As I said, they're polynomials in x and in in square root of 1 minus x squared, which is sine theta, if x is cosine theta. And they arise from solutions of the separated theta equation. So that's the equation that they come from. And so remember, this capital Greek theta is equal to something, which is a number, times PLM. And so the PLM is the simpler quantity. And if we let x equal to cosine theta, then this becomes a self-adjoint ordinary differential equation, and it looks like this, or in fact, it is this equation. And although I guess in the way we normally were writing the self-adjoint equation, we put a minus sign here, and we put this over to the sum of this at least over to the other side. And we have two eigenvalues here, basically, L plus 1 and m squared, and it depends upon how we're looking at this differential equation. And we'll see that later. The associated Legendre polynomial is related to it turns out is related to the mth derivative of the Legendre polynomial. And it's related by this factor 1 minus x squared to the m over 2. Well, this is just sine theta to the m times the mth derivative of PL of cosine theta. Now, to see why this function is a solution of the differential equation, what we do is we differentiate PL m times. And so what we're saying here, you see, is that PL, the mth derivative of PL is, when multiplied by this, is PLM. And so equivalent rewriting, in other words, this equation is the same as that. And we differentiate this twice, and one gets this expression. Well, differentiating once, you get this expression. Twice, you get this expression. Now you use Leibniz's rule to differentiate Legendre's equation, m times. So we start with Legendre's equation, we differentiate m times, we use the Leibniz rule. Remember, we learned that a long time ago. what happens then is we get this rather complicated equation. And now what we do is we put the formulas for these. We've already computed these derivatives up here, p, the mth derivative, the m plus 1th derivative, and the m plus 2 derivative. And so we can take those two expressions and put them in here, and also this expression. And if we put them, and what we see is that PLM, as defined in this way, satisfies the differential equation. And so the associated Legendre functions then are, you take m derivatives of the Legendre polynomial, and then you multiply it by basically sine theta to the mth power. And so they're simple polynomials in cosine theta and sine theta. So if you write them as, this is the mth derivative with respect to cosine theta of the Elf Legendre polynomial evaluated at cosine theta, and you multiply by mth power sine theta. That's the associated Legendre, one says polynomial, or the associated Legendre function. And one can then use Rodriguez's formula for the Legendre polynomial, and what one sees here is Rodriguez tells you differentiate L times to get PL. Now you're told to get PLM, you differentiate another M times, and so you get this expression. And well, looked at this way, it's not all that much more complicated, is it? It's just that you have an extra m derivatives, and you multiply by this square root 1 minus x squared to the m over 2. And so this works for positive m. On the other hand, it also defines the thing for negative m, as long as m is not less than minus L. And because if we had m equal to minus L minus 1, this would be the minus first derivative. And that can be defined. In fact, we did discuss fractional derivatives back in an earlier chapter, but we're going to leave that aside and just say that that m is just takes integer values from minus L up to plus L. And you can also see that PLM of minus x, well, it turns out to be minus 1 to the L plus 1 PLM of x. And why is that the case? Well, if you flip x to minus x, these complicated factors don't change, but you have you have L plus m derivatives, and they change. They introduce L plus 1 minus signs. So this is the standard definition. Then there's Condon and Shortley have an extra phase, and so if you are looking at a paper or a book that uses associated Legendre polynomials, you want to make sure whose Legendre polynomials you're using. I'm using what I believe to be the standard kind, but as I said, there are Condon and Shortley were important physicists, and some people use their convention. Anyway, what we see here is that in order not to have silly formulas, we have to have m between minus L and plus L. And m only occurred as m squared in the equation, and so that suggests that PL minus M might be related to PL of M. And in fact, it is by an overall constant. And for M not equal to 0, PLM, of course, has this square root of 1 minus x squared in it. And so PLM vanishes at x equal to plus or minus 1. And x equal to plus or minus 1, if x is equal to plus 1, that means that cosine theta is 1. Cosine theta of 1 is theta equal to 0. And if we're in spherical coordinates, that means that the associated Legendre polynomials vanish at the North Pole and the South Pole. For M not equal to 0. Now, as I said to you earlier, the self-adjoint form of the differential equation for the associated Legendre polynomial, and it's actually associated Legendre function, we can either think of L plus 1 or M squared as the eigenvalue. And if we think of LL plus 1 as the eigenvalue, then the weight function is unity. Because you remember the weight function is the thing that multiplies the eigenvalue. And since it's self-adjoint on the interval, the eigenfunctions PLM and PL prime M must be orthogonal on the interval when L is not equal to L prime. The full integral formula looks like this, and the weight function's unity, as you see, and this complicated form. On the other hand, you can think of M squared as the eigenvalue for fixed L. Then you see the weight function as 1 minus x squared. And so the eigenfunction formula is this, integral minus 1 to 1 PLM prime dx over times the weight function, 1 over 1 minus x squared. And then you get well, you get an orthogonality, and the actual integral is given by this expression here. Now, the spherical harmonics then are the product of a theta times a phi, and the phi is very simple. It's just e to the im phi, and the theta is this PLM that we just analyzed, we just figured out, but it's multiplied by this crazy square root with a minus 1 to the m. And the phi has an extra 1 over square root of 2 pi in it. These are, this is just the standard convention, and it makes other things turn out nicely. The eigenvalue equation for PLM, which we just looked at, and the one for phi is very simple. It's the second derivative equals minus m squared phi. And they tell us that the spherical harmonic YLM, which is theta times phi, satisfies this differential equation. And this is what occurs in the Laplacian in 3 dimensions. And the square root up here arranges that the integral YLM star YL prime M prime integrated over all solid angles is just unity. And when L is equal to L prime and M is equal to M prime. And I'm wondering, why is there a star here? Well, there's a star because we have e to the im phi on the phi term, whereas the theta term is intrinsically real. The parity transformation is when you flip x to minus x. And so r doesn't change. Theta goes to pi minus theta, and phi goes to phi plus or minus pi. And so under parity, cosine theta prime is minus cosine theta, and e to the im phi prime is minus 1 to the m e to the im phi. Now, this factor of e to the minus 1 to the m cancels the m dependence in PLM. So altogether, the spherical harmonics change by L, not L plus m. Remember that when PLM changes by minus 1 to the L plus m, and that's because Rodriguez's formula tells you you have L plus m derivatives with respect to x. Excuse me, somebody's at the door. Let me just see what that is. Sorry, something was delivered and I had to run out and get that. My wife is out of town. So under parity, what you have is just minus 1 to the L. And so when you talk about, say, the hydrogen atom, what you have is and let's just think of the simplest hydrogen atom, non-relativistic, no spin. The parity of the state NLM is minus 1 to the L, because the minus 1 to the m here cancels the extra minus 1 to the m in PLM. Spherical harmonics are complete on the unit sphere. They can be used to expand any smooth function with coefficients. So any function that's defined on the surface of a sphere can be written this way. And we have an orthogonality relation. And the orthogonality relation was such that the YLMs are basically delta LL prime, delta MM prime when you integrate over the unit sphere. And so you get that the coefficients here are just given by that. Putting them two together, what you find is that the sum of the y's times the y stars give you a delta function of angle. And because the area of solid angle is d phi times sine theta d theta, you divide by a sine theta here in the definition of you get a 1 over sine theta times the angular delta function. And this is sometimes written as in this way. The spherical harmonic expansion of the Legendre polynomial is what's called the addition theorem. That is to say, the Legendre polynomial of cosine theta, where cosine theta is the dot product of two unit vectors, n and n prime, n having described by polar angles theta and phi, and n prime polar angles theta prime and phi prime. Theta, of course, is the angle from the North Pole, and phi is the angle from the x-axis, which is some direction on some point on the equator. So this gives us the, well, one has this addition theorem. We'll work that out in a later chapter if we, well, I don't know if we're going to get to the later chapter here, but it's here, let me try to tell you what chapter that is. Something is funny here. I don't, whoops. My gosh. This new Apple operating system is a little buggy. I should not. All right, it's coming back on. Anyway, we don't need to know exactly where that is, I don't think. So let me skip that. All right, so where were we here? This is right. Okay. So let me make this. Let's make this bigger. Yeah, well, this is what happens when you have a corporation that wants to make everything the same as its iPhone. So let's see, we want to get back to wherever we were here. In fact, we were about to do the CMB, which is fun. Oh, Lord. Boy. This thing is not behaving very well, obviously. And it's do not I blame it on Apple's fascination with it. They want to make everything have the same software as the iPhone, and so they sacrifice other things to just, well, all right, let's see if I have well, all right, I'll just say some things about the CMB then. It's the cosmic microwave background radiation, and it comes from the radiation that was emitted when the universe became transparent. In the first 380,000 years after the Big Bang, the universe was so hot. And when I say universe, I mean our universe. We don't know what there is beyond our universe. But in our universe, about 380,000 years after the Big Bang, the temperature got down to around 1,000 degrees Celsius. And that's a temperature at which hydrogen and helium atoms just sit in their ground state, and at which the photons that are whizzing around aren't energetic enough to knock the electrons into their excited states. And so the hydrogen becomes transparent. The helium became transparent earlier, and the universe is, at this point, is 3/4 hydrogen, 1/4 helium. That's of the matter that we know of. And then it's also photons, neutrinos, and so on. And then it is this mysterious dark matter that we don't understand yet. So the universe became transparent then, and so photons that were at, say, 1 eV in energy then, now they're, with the expansion of the universe, they've been knocked down from 1 eV down to microwave energies. And I think we're talking about something like a factor of 1,000. in less energy. And so when you look out at the universe, you are getting photons that were emitted nearly 14 billion years ago. They're remarkably, they're just basically black body radiation. On the other hand, there are small fluctuations in the black body radiation, and that's what is being studied in the CMB. And so what physicists and astronomers did when they eventually got to detect the radiation coming, the microwave radiation coming from all different directions, they expanded it. Well, actually, since we do have at least my iPad working, what they did was they basically looked at they measured the radiation coming from each direction. So that is the let us say the intensity, as you can call it, C of theta and phi, and they could write that as a sum of ALM YLM of theta and phi. So that's what they did, and then of course they measured that, and they displayed that in various ways. And what they found was that it was black body radiation to within with fluctuations on the scale of 10 to the minus 5. And then if you think of the intensity, let's see, if you plot let us say L here, you get this curve that looks something like this. And this as you go to small l, this corresponds to large distances. So here we're talking about R goes as 1 over L with an appropriate constant there, and some big L over L. And so these are measurements here are at very large distance. This is the correlation between different points. So in other words, what's the correlation between the temperature correlation between these 2 points? So in other words, it's the average value of T of theta and phi, T of theta prime and phi prime, average value. And then that is plotted, and one finds a curve that looks like this. It's a pity that I can't bring this up neatly, because well, let's see, this is recovered apparently. So I can show you this. All right, sorry, it's finally recovered. I hadn't realized that. Okay, so let's see what we have here. So as I said, you can write the temperature then as a sum of YLMs, and the image of it, this gray thing is our galaxy, and or the photons coming from within our galaxy, and the red is warmer and the blue is cooler, but this is only 300 microkelvin. And the temperature, the average temperature here is around 3 degrees Kelvin of the photons coming from all those different directions. And then what they did was they took these ALMs given by, well, of course, if we write the temperature as a sum of spherical harmonics, the ALMs are necessarily given by these integrals. And then you can then sum over M, and you define this thing called CL. And if you then use the addition theorem that I mentioned to you earlier, you can see that these CLs are the Legendre polynomials times the temperature in one direction, temperature in the other direction. And these then are plotted, and this is a fit with 6 parameters. And one of the parameters, by the way, is the height of the curve. So the fact that they went through this point is not surprising. They fitted that point. The errors are bad here because the statistics is not very good at large distances, because if you can only go by pi from one angle, one theta to another theta, then you only get a few measurements, whereas there are a gazillion points that are close to each other, and so you get very good statistics over here. At any rate, this fit is the fit from what's called the lambda being the density of dark energy, cold dark matter prediction. And so the idea is that about 3/4 or so of the energy density of the universe is dark energy. It's just a constant, and it could be just the energy of the quantum fields in their ground state, or it could be something else. It could be due to the potential energy of some scalar field that hasn't yet relaxed to its ground state, maybe trapped in some tiny minimum. Anyway, it's mostly dark energy, and then most of what's left is dark matter. And the dark matter is what a certain German physicist called it, astronomer called it back in the 1930s, but it's really transparent. It's just matter that doesn't interact with the electromagnetic field to any significant extent, and so it doesn't give off light to any extent and doesn't absorb light to any extent, and so you can't see it as transparent. But it's not dark in the sense that it would block light from that's coming from behind it. So what we've got here is, in a sense, a triumph of the lambda cold dark matter model, but we have two mysteries: what is dark energy and what is dark matter? And it's wonderful to have mysteries, because otherwise physics would be quite boring. But on the other hand, these are mysteries, and they've been hanging fire now for for many years. It was 90 years ago that transparent or dark matter was first discovered. And the idea is that you have these galaxies that are moving, that are in clusters, and the gravitational field of the cluster isn't strong enough. If we just think of ordinary matter and the light of the gravity of the stars, there aren't enough stars to cause the galaxies to be able to move as fast as they are. In other words, if they were moving as fast as they're moving, they wouldn't be bound in they wouldn't be gravitationally bound. They would have sailed off. So there must be more matter there that we don't see, and that's called dark matter or transparent matter. But what Adam Rees and Saul Perlmutter and this guy's name I keep forgetting discovered about 20 years ago is that the expansion of the universe, which we thought was slowing down, is in fact accelerating. And the reason it's accelerating is that empty space has energy. And in fact, the energy of empty space is more than the energy of the average energy of the universe, counting the dark matter and the matter that we know about, the matter that's not transparent, the matter that does interact with light. Well, we're basically out of time. I'm glad that the computer has finally recovered. It's very, very strange. I don't understand this at all. And I mean, I don't understand why the files disappeared, and I am even more surprised that they came back, because normally when something goes wrong with the computer, it goes wrong until you fix it. And I didn't do anything, it just repaired itself. All right, well, I'm going to stop sharing. Let me check, though, chat. Maybe somebody said something in chat, and I don't see anything in chat. So have a nice weekend. I posted the new homework assignment. And remember, you have to look at the class notes to see what one of those homework problems is, but it's not for the current assignment, it's for the one after that. All right, well, I'm going to wish you all a nice weekend, and we have some sort of a colloquium tomorrow, and I'm going to stop sharing, and have a nice weekend, everybody. See you on, and Monday, the office hours are going to be 4 to 6, not 3 to 5, and they're going to be via Zoom, and I'll send you a Zoom link. Bye.